Welcome to the latest edition of Astraveo's Coast-to-Coast podcast of science, astronomy, and the world around us. My name is Joseph. He's David, and we're just two friends who happen to be professional astronomers with a love of telescopes, astrophysics, and all things science. Today, we've got something really special for you guys. We're going to be doing a focused session on the latest result from the Event Horizon Telescope collaboration, which both David and I are part of. We'll be discussing the press released images from earlier this week, where our collaboration presented the third ever image of a black hole, a new image of the M87 star system. Let's dive right in.
All right, well, thank you for that introduction there, Joseph. Very nice, very succinct. So you mentioned that we are part of the Event Horizon Telescope collaboration. Can you elaborate your role in the collaboration, please?
Sure. So the EHT is a collaboration. We make images of black holes using a global network of telescopes. Part of that process involves taking our data and making images and making measurements using the data. And so that's my role. I help make the images that you see like in the press releases and the media and stuff. And I also help with the measurements. So using models to fit the data directly and attempt to extract physical information about the black holes that we study. What about you, David? You got a very important role as well.
Well, I can't compete with that. Holy cow. They should do everything. Joseph is the EHT collaboration.
That's super not true.
So my role has changed a wee bit over time, but I started out in 2017, late 2017, as the program manager, essentially keeping an eye on the process flow, the scheduling, the funding, the allocation of science teams, data analysis teams, all those kind of things. Essentially making sure that instrumentation and people were where they were supposed to be, when we needed the telescopes to be observing. And I jumped in a wee bit on the science. I've been around a long time, as you know, so I've got a little bit of cosmology in me somewhere, but certainly not at your level, of course. And then into helping interpret the papers and doing some editing and that kind of thing. And now I'm more of a sort of array operations person, just again making sure that the instrumentation and the people get to the right telescopes at the right time.
Yeah, minor stuff like making sure everything's working and people are doing their job. Just little things, just the most critical aspects of the collaboration.
Well, at least getting the photons into the astronomers' hands. It's pretty cool.
Coaxing the astronomers into the telescopes and the photons into the other end.
Pushing them. So, given that we've got these new images coming out, in a sort of grand old style, what's new, Pussycat? What's going on for the collaboration?
So, a really, really exciting new result. So, most people have seen the very first image of a black hole that was from the 2017 observation campaign. And then in 2018, we turned on the telescopes again and pointed them at M87 once more to try to get a second image of the system a year later. And so that's what's this exciting new result this week. So, we've got this new image, and the ring is still there, just in case anyone was worried. But it does look a bit different in an exciting way that we can do some science with. So these are really the big results that came out this week. And it was a really, really exciting press release, conference, and everything.
Yeah, right, absolutely. Well, I'm really glad you mentioned that because, and I know I'm a big proponent of this, both in my sort of life and my teachings, is that it sounds like what you've described to me is a big part of the scientific method, and that's the reproducibility of your results. And so if an experiment takes results 1 year with a given setup, in more or less the same setup, if they take results another year and the system has not drastically changed, one might expect something somewhat similar.
Yeah, exactly. And this system is a classic example of one where we can apply this approach really effectively. The M87 black hole is so large that it evolves over the timescale of days, which means that over the course of a year, you might expect a little bit of evolution that we could see in the images. And that gives us information about the astrophysics surrounding the black hole. But the fundamental properties of the black hole, like the mass, for example, over the course of a year basically don't change at all. And so things like the size of the shadow of the black hole, the sort of fuzzy orange donut, we don't expect that to change very much. And so this is a perfect way for us to validate our results from the previous year while simultaneously doing new science. And it's amazing that effectively a 4x4 pixel image can communicate all of that.
Absolutely. No, I couldn't agree more. So that brings me to another point, and I've asked this question several times during these podcasts. Who cares? Where's the scientific interest? Where's the driver? apart from the 350 odd people in our collaboration, who really cares about what we're doing?
So, I actually I think that the black hole stuff that we do is one of those things that, almost everything else, you're like, how does, your average Joe get affected? It doesn't change the price of bread, price of eggs is still $40 a carton. So, but I think the black hole image stuff is one of those things that, like, for some reason, everybody loves this stuff because I think it represents like the boundary of human knowledge. Everybody kind of knows that black holes are like these weird exotic things, even if you know nothing about them. And if you ask like 100,000 people what they knew about black holes, the most common sort of fact that everybody knows, even if you just like kind of intuit it, is that light can't escape, so you can't see them. And so taking an image of this thing that nature is like, you're not supposed to look at that, it's a very human thing to do. And I think
Mhm.
from a purely like public interest perspective, that's a big driver. But it's also really interesting from like a humanities body of knowledge perspective, right?
Yeah.
The black holes are kind of governed by general relativity as far as we know, but once you get down to that singularity at the center, the laws there start to conflict. The explanations, the models we use to explain it start to conflict with the other very successful theory, quantum mechanics. And quantum mechanics and general relativity are the two most successful theories in human history. Like they've hundreds of over 100 years of experimentation to crazier and crazier precision for both, and we haven't found a single instance where they're wrong. And every time we thought they were wrong, it turned out we were just wrong about how we were interpreting something or how we were designing some experiment.
Yeah.
And so there are these two very, very successful theories, and we've been able to sort of keep them separate because they disagree in a fundamental spot, the center of a black hole. But we were able to keep them separate because we were like, well, black holes probably aren't real. And actually, maybe you can look at this disagreement and say, here's an object that makes these theories conflict. It's probably not even real because nature seems to like these two theories. But now we know they are real. And every time I look at that image of the black hole, it's like inside of that thing, one of the two theories that we know should be correct breaks down. And if it's quantum mechanics, that's really, really bad. And if it's GR, that is even worse. So it's like a preemptive, uh-oh, we have work to do as a physicist, um and it's a reminder, honestly, maybe a like a reminder of humility. Like, we don't know everything, and that's an image of a lot of stuff that we have no idea what's going on. So
Yeah, no, absolutely. Absolutely. Couldn't agree more. I think for me, one of the fundamentals I think about, and I'm going to ask you a very easy question in a second, but I think it's an awful lot of people will ask this question as well, is we hadn't, and we're spoiled with the technology we have access to, the computing power, the very sort of intelligent people in our collaboration. We're completely spoiled. But don't forget, we've only been imaging black holes for 5 years, and their existence has been theorized for, let's be generous, 80 to 100 years, depending on when exactly the person came up with it. But the thing I always think about is how, the image proves that black holes definitively exist. Well, they were previously theorized, and we see we see intense X-rays coming from them. We see stars orbiting them with these very extreme velocities. That has to, imply there's a very massive object there that you can't see. But
really, it's a
this,
gravistar, David.
yeah, well, that could be that. But essentially, we've sort of got to the point where we have proof of this very complex system that was for a long time just theorized. And so the second part of that, and you said something very interesting to me, is that black holes, we haven't been able to see them. For the average Joe and Joanna on the street, the question I would have if I was one of those people without our scientific education that we've been so privileged to have received, why can we see this black hole? Because I thought inside black holes you don't see any light at all. So I don't really understand that part.
It's
As
true,
well
and
as perhaps,
it's a really important nuance. You're right. Once a light gets inside of a black hole, it can't escape. But because the gravity of a black hole is so strong, there's a region outside of which that photons can orbit either multiple times or just once before they escape eventually. So basically, like inside the event horizon of a black hole, you're right. No matter how fast you're moving, no matter which direction, no matter which god you pray to, you're not going to escape the black hole. But just outside of it, if you're moving at the speed of light, like, light. If you're moving at the speed of light, like the light that enters our telescopes, and you have just the right trajectory, just the right angle, you can get out of the black hole. And it turns out the right trajectories and the right angles required correspond to photons making certain loops around the black hole. And that's what
Yeah.
produces these rings in our imaging, this lensing of photons that almost get sucked in but don't. And
Yeah.
so we call it the black hole because that's the best we can do. What we're really seeing is the shadow of the black hole on the
Right.
glowing accretion matter around it. And some people might say,
Right.
well, it's not really the black hole itself. And that's kind of true in the same way that, look, you're not taking a picture of the Earth, you're taking a picture of the crust of the Earth.
Yeah.
But for all intensive purposes, this is sorry, I'm so sorry. But this is this is basically an image of the black hole. And I think it's like in terms of what we're imaging, although our images will get better, higher resolution, and we'll be able to see more and more extraordinary things. For us, this is the best we'll ever be able to do without going inside of a black hole, is imaging the photons that are just about to fall in.
Yeah, that's right. And I think, I mean, we played good cop, bad cop there in this, the science part of it. But I think that's fundamental for our audience to understand, is that we're observing emission of material or photons from outside the event horizon.
Yeah.
As you rightly said, they're being orbiting the black hole and being lensed and so on. Okay, so I think we've addressed the question of why do we need a new image. I really like that part of the discussion. Was our instrumental setup the same? Did anything change from 2017 to 2018?
So it did change quite a bit. So for those that don't know, the EHT is composed of a bunch of component stations, and those stations connect together to form the baselines that we collect data on. And so what stations are active, et cetera, produce different sets of baselines. So the interferometer can look quite a bit different from year to year. And so in 2017, we had a bunch of sites, but in 2018, we added a telescope in Greenland at the GLT that gave us these extra long baselines, especially from Greenland to Chile. And so I have a map that I can show of what
Oh
that
yeah.
looked like. So this is a map of the Earth showing the configuration of the telescopes in 2018. And so basically this site up here, Greenland, this one was not active in 2017. We had not incorporated this into the array yet. And so all these baselines that connected to it, all this extra data, we didn't have. And so that's why this new image is, we've got even better stuff going on than the first one. And you'll notice that there are these sort of pseudo baselines connecting to the South Pole. So because the M87 is in the north, it's actually not visible to the South Pole ever. But one of the objects we used to calibrate it, which we'll talk about later, was this object 3C279, and that was visible to the South Pole because it's it's farther south than M87 is. And so it's these baselines that form this UV coverage map, which is basically a map of where in this thing called Fourier space we're able to probe data from. And the only thing you need to know about it is that the more data you can collect there, the better. And so we were able to get a little bit more data than the year before. But largely, the array configuration looked similar with the addition of this one site.
Yeah, no, that's a good observation. But the GLT does turn out to be really important because, as you rightly said, we get these very, very long baselines between Greenland and northern Chile down to Apex and Alma, medium baselines over to Pico Veleta in southern Spain, and then this really nice baseline out to the 7mm array and the James Clerk Maxwell telescope over there in Hawaii. So really important site. And in fact, just looking at it, it does create an awful lot of baseline triangles for closure.
It does.
That's really, really nice. And obviously with the Mount Graham telescope there in Arizona, the SMT.
I remember longer is better too. So
yeah, that's right. It increases the effective aperture of the global telescope, the Earth-sized telescope. So absolutely, it's a really important site. So I'm really glad you mentioned that. Thank you. It turns out
I've got a cool one for you too, David. Another really exciting thing that GLT added that I'm personally excited about. It's a little bit technical, but it's kind of easy to understand. So from either a time domain or a calibration perspective, it's very, very useful to have these stations that are distant from the array, like SPT or GLT, because it creates these baselines like GLT to SMA or GLT to SMT or GLT to Pico Veleta that are very, very similar in length, but not orientation. As the Earth rotates, these baselines will basically begin to overlap, and so you can
Yeah.
calibrate them to each other, or look at them occupying the same part of UV space as a function of time, and then you can say make time domain measurements of them. And so I just find that a little extra tidbit super cool about why this particular station was important.
No, absolutely. That's a great observation. It's actually sort of like taking a slice through the UV diagram and cutting through multiple baselines. You get this sort of internal network calibration. It's very, very nice.
Exactly.
Yeah, no, absolutely. That's a really important diagram. I think. Thanks for that. The data rate, by the way, at which we were taking data for 2018 also increased, I believe. So that we were
Yep.
taking more data, and more is generally good because it just increases your the spatial resolution goes up with this extra Greenland site, but the temporal resolution goes up if we can observe the data more quickly and record more of it. So we actually increased the array's performance, the sort of this global network, considerably in 2018, actually.
And that makes the EHT, the Event Horizon Telescope, now the highest data collected per night of observation of any experiment in astronomy ever. A title previously held by the Event Horizon Telescope in 2017. But it is crazy. We collect like a petabyte of data per night, which is
Several
a
petabytes.
thousand terabytes. Like, it's
Yeah.
ridiculous.
Oh, it's huge. It's huge. It's huge. Well, just putting all those data together is just a monumental task that our calibration and correlation group do a phenomenal job with. They really do.
It's true.
And I think we should mention, I think we've mentioned this before on a previous podcast. This is not a one-person band. There are
No.
300 plus of us. It takes a standing army to make these kinds of observations, with planning, having people at the telescope, and then the sort of very, very hard work starts then of putting those data together, analyzing the results, doing the image analysis, image correlation to just basically ones and zeros. Very, very difficult process. And so it's an enormous job that we have over 300 people doing.
Yeah, it's truly a collaboration effort, a global collaboration as much as just a global
Absolutely.
telescope. People, it's easy to think like, oh, we take the data and then a year later we produce an image, but it's actually like building up the array took 20 years of steadily
Yeah.
better and better observations, and like these dedicated people that devoted their lives to this project, which is just amazing.
Yeah, absolutely amazing. Well, we took these data in early 2018, and the results just came out. So nearly 6 years later, and one could think, oh, that's such a long time. What's going on? But just the sheer quantity of data, and then of course we were working on the 2017 images for such a long time. It takes an enormous amount of effort for the data to go from telescope to scientific research papers. And so
Yep.
luckily our collaborators and the telescope stakeholders and the funding agencies realize this. They realize this is no small endeavor.
I've got a quick question for you, David.
Yes, sir.
Last year, the 2017 data were taken in, I think, March, and or no, 2017
April,
data were
early
taken
April.
in April, yeah, and these
Yeah.
data were also taken in April. Why do we keep doing it in April?
Well, that's a good question. Maybe we sort of like the Easter collaboration, if you're. So I think the biggest reason is we are constrained by the objects themselves. We tend to observe two black holes, as you rightly said, so M87 and Sagittarius. And they occur, the perfect time for observing M87 is about March, April. It's 12, I think it's 12 hours in right ascension. So that does put it perfect for March-ish. Sagittarius is perfect for June, July, because of its right ascension being about 18 hours. However, we also have some problems that in the northern hemisphere, of course, we get severe winter. So obviously, especially in places like Greenland and obviously Pico Veleta and on top of Mauna Kea in Hawaii, if we were to observe in the dead of winter, Sagittarius A star would not be as visible. M87 might be, and you would have cold weather, and cold weather is generally good because humidity drops out the air, and humidity is great for giving excess infrared emission from the sky. However, more nights are cloudy. You get longer nights, which we generally want, because when the sun rises, you get turbulence in the atmosphere, and that sort of seeing distorts our images. So we try to balance everything. We try to balance longer nights, so we tend toward northern hemisphere winters. We tend to go toward March, April observations because it's perfect for M87, pretty decent for Sag-A star. The length of day and night is about equal. It's near 12 hours, of course, at the equinox, 21st of March. And also you have a nice balance between northern and southern hemisphere weather systems so that you don't get too much turbulence in the atmosphere, nor too much sort of precipitation. And in general, humidity levels are not yet so catastrophic that you get this enormous background emission from the sky. So some of it's geopolitical, some of it's meteorological, and some of it is just for convenience of observing those two objects on the sky.
I love it. That's perfect. And it's like I think you brought up an important point, which is, we only have 1 week to really 2 weeks of time throughout the whole year
Yeah.
to observe these things. And so it's not like we can just have the telescopes on at our beck and call throughout the whole
No,
year.
that's right.
It's only this one, like, time per year that we get to turn them all on. So it's like you said, it's really critical that we that everything go perfectly.
Yeah, well, it's a really good observation you just made, in fact, in that all the telescopes in the system and the global network we're talking about here, all 9 on this map, they are not available to us all year round. We have time allocation on them. That's the formal expression, and we have to apply typically. So there are these things called time allocation committees, where all astronomers and even members of the public can apply to a science project on a given telescope with a given instrument. Well, the Event Horizon Telescope also has to apply for time. We don't have guaranteed time on any of the telescopes actually, and so we submit a science proposal. Normally 6 to 9 months before the observations. We tell the telescope stakeholder committees why we want to do the science, what they'll get out of it, what we'll get out of it. And obviously, at the moment, this project is such high level; it's so important in terms of scientific return. We generally do get the time. We're able to justify why we need their facilities. But even 10 days, 14 days on a telescope is an enormous allocation. It's very, very large. And so for really expensive sites to run, such as GLT, because it's such an inhospitable climate, SPT again in Antarctica, ALMA, one of the biggest arrays on the planet, very, very expensive sites to operate. You're talking hundreds of thousands of dollars per night. It's a really big deal for us to get 10 to 14 dedicated nights on a given observatory. So I think you brought up a good point there.
Love it. That was a perfect breakdown.
Yeah, that's important. Okay, I firmly believe, and I know you disagree with me, but I firmly believe that you are much more ensconced in the science than me, and you wrote one of the papers yourself and contributed significantly to a lot of the others. Why don't we tell the folks listening in what exactly we're doing? How did we do the science? How did we do the analysis?
Yeah,
How
so
did
let's
we
pull
turn?
up one of the images.
Let's pull up one of the images. Let's have a look. I think that's what
So
everyone's dying to see.
these are this is the old image, the 2017, the old, out of date,
Yeah,
burst into a
that's
black
right.
hole.
Yep.
Who cares?
Yep. On the left hand side, this is 2017.
Yep. And then on the right hand side, this is the new one, the new kid, the
Yeah,
cool kid on the block.
the
So this
cool
is from
kid.
the 2018 data, one of the days. And as you can see, the first and most important thing is that the ring is still there. We still
Yep.
see this emission profile with this depression in the center, and that is super critical, right? That's the big science result, is that there is evidence of a horizon, and we still see that the second year. So for those who are concerned that either there was an imaging fluke, or like maybe it was just a fluke of the astrophysics or something, a year later that same feature is still there, and it has the exact same size, which strongly indicates it's a remnant, it's a relic of the black hole itself, and not just some fluke, either an imaging problem or just an astrophysics fluke. The second thing is that, yeah,
Or a problem with our algorithms, that we
right.
produce an imaging algorithm which is just by sheer bad luck or just poor design is giving us this circular ring structure.
Exactly. It's super unlikely that it would do it 2 years in a row with two different data sets, two different arrays.
Yeah.
And so the big thing, though, and the exciting difference, so that was how we validated the first image, but the image does look different, as you can tell. So we're not in the case of the office meme with they're the same picture. We can spot some differences here. So
Yep.
the April 11th image from 2017 shows this sort of even brightness distribution towards the south that's kind of biased towards the southeast. And that always trips me up. East is on the left on the astro
Yep.
images because you're looking at
Yep.
the celestial sphere from
That's
below.
right.
I always mess that up. But as you can see, that distribution has moved. It's kind of moved from the left here over to the right quite a bit. And where there is
Well,
this, yeah.
sorry to interrupt. Yeah, just an interesting scientific point there. It hasn't necessarily moved. It could have, but it could be just the old emission feature could have died out or been dissipated, and this is a brand new emission feature.
That's a really, really good point. Thanks for clarifying that, because there's another nuance we can point out too, which is that the light crossing time of M87 is about, I think it's like on the time scale of days. And so over the course of a year, if this is, like, for example, a feature really moving around, it could have moved around dozens of times, and this just happened to be the next spot we caught it. Although I think it's unlikely that's the case. I think it is more likely what you said, that it's like emission just varying around the object, but but it's still some level of variation in a clear sort of rotational direction. And so this allows us to like see the black hole evolving over the time scale of a year. And so there's lots of really cool science that we can do with that.
Yeah, no, I couldn't agree more. I think also had it looked identical, I would have been worried.
Yes, that would have been. I would have been much more worried about that.
Yeah, that's right. Yeah, absolutely. Because as you rightly said, with a light crossing time of a couple of days, and who knows what the rotation period of this thing is, one would have had to have been just ridiculously unfortunate for the images to look identical.
There's like a certain level of variation that you can expect when you look at the different imaging algorithms themselves. And if it had been within that level of variation, that would have been very concerning.
Well, no, absolutely. Great point. And in fact, you're collecting a whole different set of photons that have error bars themselves, and maybe certainly with the new instrumentation in the array, to get the sort of near exact same result would have been problematic for our scientific method, I think.
Yeah, but we did see a rotation. Yeah.
Yeah, absolutely, of course. So here's something that's always driven me, and you've heard me talk about this in some of the imaging groups, is how do we know what we're looking at is anywhere near the truth? Because obviously we didn't have a version of an image of the black hole before. So how do we know this looks like what it actually looks like?
So that is a really, really deep question. A question about, like, how do we know the image is correct? We're taking an image of something that's never been seen before, using a telescope that's never been used or calibrated before. And although that's no longer true for this image, but so now we actually have something we can compare it to the previous image it got. But this is a more generic question of how do we know with this kind of answer, what can we do to really make sure that we're getting something that we believe to be correct? And that is such a fantastic question, and it's really multifaceted. So there's multiple approaches that we've done to validate and ensure the correctness and validity of the image. And there has been some, discussion online, as there always is. It's a black hole image. How do we know it's correct? Is there, consensus in the community, stuff like that? How does the community trust our results? And so this is what we basically put forth to convince people. So first and fundamentally, we have the data are worked on by separate teams of people that each bring their own assumptions and tools to the problem. So, for example, there are different imaging algorithms that you can use to reproduce these images. And we have 4 teams of people that use 4 imaging algorithms that are basically grouped into 2 types. And they each bring their own expertise, assumptions, prior knowledge about the object, and make their own independent image blindly. We then give these images to a computer algorithm that gauges for us how similar they are, and it tells us first what percentage alike they are. And if the percentage is really high off the bat, then we know that even with our different assumptions and our different algorithms, we're getting the same answer out of the data that tells us the data are resistant to our prior assumptions and our tools, our humanity. And that's a really, really good check. And for both of these images, these 4 separate teams came together and produced basically the same results. There were some minor differences, but the salient features were there in all the images: a ring of about 40 microarcsecond diameter with a brightness asymmetry to the south. And so that right off the bat is one easy check.
Yeah, it should be made obvious. I don't know how clear it was. Very nice explanation. But those 4 teams do not talk to each other. They're so-called blind imaging. And so, for instance, the group you were in, you worked together as a mini collaboration, 13, 15 people. And then, but you didn't talk about your results or your methods or your priors, sort of the input into these theoretical models. You didn't discuss those with the other three groups. That's right, isn't it?
That's correct. Yes. And we were
Yeah.
extremely strict about this. So I actually was one of the organizers for the workshop in 2018, where we produced the first image of a black hole. And we had people literally hold up in separate rooms, and we would take put like film on any windows or openings so that nobody can see inside. And because this was such a big event, there were documentary film crews and stuff filming us, a la the penguins from Penguins of Madagascar. And so sorry. And so one of the documentary film crews attempted to subvert the rules we had put in place to try to restrict any communication or preliminary images from getting out. And they tried pressing up their cameras to a hole we had left in one of the windows. And even though they were just trying to do it because they were trying to get an image like for like an exciting like sneak peek behind the scenes preview or whatever, it was so critical that the image not get leaked to each other, like to the separate teams, that we kicked the documentary crew out after that. So just for that single act, that was how strict we were about not letting any communication pass between the teams. And no team saw each other's images until after we had run it through this computerized comparison to assess how similar the images were to each other.
That's great. Has that documentary crew returned from their stint at the South Pole Telescope now as punishment?
from their imprisonment in the Phantom Zone.
That's right.
No, they're still out there going, I'll find him.
I'll find you. I'll be back. Super important, this, Joseph. Really important point, and I'm really glad you made a big showing of that, because I think that's one of the things that would again be destructive to the scientific method, is to minimize as much as possible the human input, the biases, the preconceived ideas we have sometimes when building our algorithms and doing our data analysis. So I think having those 4 separate teams really did, at least as well as we were able to do with the data in hand and the algorithms we had available to us and those we developed, that we were able to minimize those biases, minimize cross-contamination between teams. And also, yourself, if you ask a question of somebody but you sort of give them a hint along the way, they're probably going to find the answer that you want them to find. And that is completely unscientific.
Yes. And that's a serious problem that we had too, because we kind of knew what we wanted to get. Not what we wanted to get, but we kind of knew what we expected from the physics. We had simulations.
That's right. Yeah, but I think working scientists try to avoid this at all costs, is we don't work toward an answer that we already have in mind. We work toward the answer. And sometimes it's disappointing. Sometimes it's not either the answer you want or you prefer, or it doesn't look good for a flashy press release. But that fundamental honesty to say, we're going to work toward what the data give us, what our fundamental training has given us in mathematics and physics and astronomy. And you get what you get and you don't get upset. And so I think that separating those 4 teams was really a fundamental part of the scientific method that we followed quite rigorously.
It was, but it wasn't the only way we validated the images. So part of the problem is, while the 4 teams on the face of it sounds like really good already, and it is, let's consider a simple example where you have 2 possible but distinct images that could fit the data, which is not uncommon in VLBI.
Absolutely.
We don't know if that's going to be the case going in, but let's say you have 2 distinct images. Let's say there's if you give any random imaging team the data, there's like a 50-50 shot they'll get one image or the other. Even with 4 completely independent imaging teams, there's still a 5 to 10% chance that we'd all accidentally get the same image, whereas there was another one hidden in the data. So we had to address this very specifically, and we actually targeted the bias that we all knew we had, which is that we knew from simulations that if there was a black hole there, we'd expect it to be something like this, where there's this ring and there's a depression in the center. And that by itself is not problematic, that we had a good prediction, but we have to make sure we avoided it. And so what we were worried about was that our imaging algorithms, we would either subconsciously or consciously influence them to taking whatever image we found and putting a hole in the middle. And so we designed a suite of tests that everybody had to go through first in order to make sure that the imaging algorithms that we created avoided these kinds of pitfalls. And so uh, actually, this is sorry, I don't mean to flick around, but this is exactly what we're talking about. So here we have the different imaging teams, and these are also some modeling as well. But here are three separate imaging algorithms: Smiley, EHC imaging, and DiffMap on the different days of data. And what you can see is that they all produce the same structure in the images. This ring with the exact same size and this brightness distribution in the exact same direction across all imaging bands, across all frequency bands, across all imaging algorithms and modeling, which is a completely different beast from imaging. We get the same result, and this is what we're talking about by that validation.
Yeah, nice.
So, but regarding addressing our specific biases, this is one of the ways we do it. So we design these things called synthetic data tests. We create ground truth images that we know the correct answer to. So here's a crescent, here's a ring, here's a binary source, and here's a disk. And you might ask, why did we pick these? And the answer is they all produce visibilities that look pretty similar to the real data. And so just by looking at the data, which is the yellow data points in this figure over here, just by looking at the data where it has this clear peak and then fall and then bump, that Bessel function, that behavior is called a Bessel function. And it immediately tells us that it probably has to look like one of these four images. And so by creating these four synthetic data tests, and then simulating how an observation would look with all the intricacies and noise and array configuration of the real EHT, we can take this data without like saying this is a crescent ring double disk. We can take this data without telling anybody what it is and just give them to the imaging teams and see what they recover. And if they were subconsciously influenced to put a hole in the middle, for example, to reproduce a shadow, they wouldn't know that the disk did not have a hole in it. And so their reconstructions would have a hole. And so what we see is that this is not the case. For each of the objects, we're able to extremely accurately recover what the original source looked like. And you can see there's smaller features that we don't trust that they don't appear in the images. And that's why when we look back at the images, we don't say, for example, oh, we trust this tiny little knot that appears, but we trust the overall features, which is that, for example, this crescent has a bias towards the south. And in the images, we see a bias towards the south, a bias towards the south, a bias towards the south. This ring has a uniform distribution. And you can see it has a uniform distribution here, here, here. There are these little knots and knobs, but they're evenly distributed. And same with the binary and the disk. So this is a hugely important approach we have, these synthetic data tests for testing our algorithms in a scenario where we know the correct answer. And that's a very, very important validation.
Yes, I think that's what I was getting at earlier about the ground truth. How do we know what we're reproducing is truly representative of the physical conditions around that black hole? And these two plots explain this perfectly. Actually, you did a good job there. That's very, very nice.
So that's with the I'm very happy to say this is still not the only way we test this. So one of the other things that we do is we have this thing called a calibrator source. So as we're imaging M87, as we're the telescopes are pointing at M87, every few minutes they turn and they point at another object that we actually know what it should look like because other people have imaged it just at longer wavelengths. And so when we take our imaging algorithms, theoretically, because the array configuration, everything is exactly the same, the imaging algorithms and the settings we find and that we use and the assumptions we make should apply equally to the science target and its calibrator. So when we point at the science target and the calibrator, if we use the same imaging algorithm to reconstruct both, the calibrator should give us the image we know to be correct based on other observing campaigns at longer wavelengths. And so in this case, M87's calibrator was a quasar called 3C279, which we've actually published research on in the past. And we found that when we pointed at M87, when we pointed at 3C279, we get the same images that everybody else in the community gets, just with higher resolution, basically. And so that tells us that, okay, the imaging algorithms are working to reproduce something else that other people have seen. When we take the exact same algorithms of the same settings and the same everything and apply it to M87, we get this new image. That gives us a huge boost of trust. So it's, and honestly, I could keep going and going and going with the ways we validate, but this is an incredibly, incredibly robust result. And this is just how we validate our results internally. We're not even getting to the point where independent teams have come in, taken our data after we published and reproduced the results for themselves and seen and gotten the same thing with minor differences. And those differences have then gone on to drive the field as a whole as to how we what's wrong with our algorithms and stuff like that. But everybody gets the ring with the brightness asymmetry to the south.
Yeah, absolutely. Now, that's a really good point. And in fact, you and I discussed this earlier this morning before we came on air, is that the consensus among the community that they are able to reproduce our images, at least to reasonably good fidelity with the same data set, is really, really a good indication that we are at least eliminating the biases in ourselves and in our processes as best we can. Now, does every single person in the community reproduce what we reproduce? No. Does every single group agree with us? Not necessarily, but the vast majority do. And so that really gives us reassurance, while acknowledging there could still be some issues to iron out, and we have improvements to make, of course, that's the nature of science. The fact that so many groups around the world are able to reproduce our images, are able to follow a similar scientific method and get almost the same results that we do within the errors, at least, means that if there are one or two groups that aren't able to reproduce our images or don't get the same results, they are probably either doing something perhaps not as well as we are, or their imaging algorithms aren't quite as developed as ours. But I think it really does show that we were very rigorous in the beginning in eliminating our biases, is setting ground truths and understanding our algorithms as best we were able to.
I love the way you put that, and it really is like, it cannot be overstated. The vast, like overwhelming majority of the community has tried to reproduce our results in a number of different ways, and has come to the same conclusion. And the disputes are often more about interpretation than like it's largely undisputed in the community. Like the vast majority of people in the community agree we found a ring with a brightness asymmetry. The papers that come out disputing it are excellent, and they actually make us think deeper about the physics behind it. Like, is what we're seeing exactly as we interpret it? Is it the shadow of the black hole? What specifically does that mean? And you can get really specific. Like we said before, these are photons that are orbiting around the black hole. It turns out each of the photons, as they orbit around the black hole and complete a higher and higher number of orbits, leads to a slightly different image on that all a slightly different image each time, that all add up to produce our image. And that's a really, really interesting subtlety. And so that's the kind of stuff where, like, that's where the disputes really lie, is what precisely are we seeing in the context of general relativity and this object. But it really is across the board. It's one of the, I think you could argue it's one of the most robust results and like reproduced results just in the history of astronomy. Like I don't know in terms of the ratio of like how little was known prior to how trusted the results are now, given that we had an instrument that's never been used before, never been calibrated on an object that had never been seen at this spatial resolution. The way the level of trust the community had in our results, due to the literally hundreds of pages of validation that we published, and the transparency we had, right? We didn't just publish the data for other people to work on. We published our scripts, our full imaging algorithms. You can go home right now, and maybe we should have an Astraveo tutorial. You can go home right now and run these scripts and produce these images yourself and play with the settings and see how it affects the outcome. And so it's just such a robust result. I love working in this collaboration.
No, see, that's phenomenal. I do like that aspect of it. In fact, I think you mentioned a really important point, is that we were scientifically honest. We said, here are the data, here are our algorithms, and here's how we operate them. You go and to other scientific groups, go ahead and see if you can reproduce what we did. See if you can do it better. See if you get some anomalies that we didn't notice. And again, as you rightly said, for the vast majority of groups around the world, they were able to reproduce our images really quite well, and make the same physical inferences about black hole size and spin and magnetic field and those really important physical characteristics that do define the cosmological interpretation of black holes. So I like the way you put that. That was good. That was very good.
It's such, and I love what you added there too. It's really, you're right. It's really an important point.
Yeah, I mean, one thing that used to bug me actually is that I would go to scientific talks or conferences, and people would present a graph or some plot, and it would have these beautiful data, and the correlation between the data was wonderful, and you'd show some plot, some model on top of the data to interpret it. And I'd always think, where are the bad data? Because we all get bad data. It could be that the instrument, the instrument wasn't doing what it's supposed to. The telescope pointing couldn't have been quite right. The humidity jumped up in the atmosphere. There's all kinds of reasons, right? Or you could have just made a mistake, which holistically we must do as scientists. But these plots look so perfect and pristine. So I would ask the question of the author or the presenter and say, why are your data so close to your model? Where are the pathological data? And they would reply that they removed them from the plot. And I said, well, I think that's scientifically dishonest. You should show your poorest data as well as your best data. Because if you have lots and lots of poor data, it shows that there's a problem in the experiment or your analysis of the data. And so I made a firm sort of commitment to myself as a young scientist, sort of your age scientist, and said, I'm going to publish all my data, warts and all, the bad ones, the good ones. Can you explain the bad data? Yes, that's good. It was cloudy, or the telescope operator fell asleep, or you spilled coffee on the computer. It was all kinds of silly reasons. But you show your poor data as well. And most of them will always be excluded with things like large error bars, which, yourself, mathematical fits will essentially ignore. But showing those poor data is very, very important for scientific honesty. And it sort of really enhances your reputation as a scientist.
And honestly, that's how I know you personally, and that's how you conduct yourself as a scientist. And it's had a big impact on me as a budding astrophysicist that has inspired the way I want to approach my work as well, directly inspired by you.
Oh, thank you, my friend.
And I did hear there was a great quote in the HG collaboration at one point when we were discussing, how much of the bad data to include or not, and the overwhelming consensus was there's no such thing as bad data, only bad scientists. And I kind of it's a little harsh, but like the idea is like, there's no such thing as bad data. If you have bad data, then you have procedures and models that correct for it. If you're just throwing out data that is making your life more difficult, then you're not really following the scientific method there and treating your data the way it should be.
Yeah, right. I think that's one. Actually, I'm really glad you said that. I think that's one of the points I was trying to make, but not quite as eloquently as you. Is that when one as a scientist starts including data because you're sort of afraid of the interpretation or how your colleagues will feel about you, or you think it'll be a good data point to sort of prove your point. Again, that working to a result is absolutely what we do not try to do. We always try to see what the data tell us, and we try to get that ground truth. If you're expecting 1 star plus 2 stars to equal 3 stars, you will work toward that. Whereas if you're working toward what does 1 star plus 2 stars give us, then that's a whole different scientific experiment. And it's fundamental that we don't do the first case, we actually do the latter. We work toward what we think is scientifically best. Because if you start impinging or imparting, that's probably a better word, your own humanity on the data sets, it makes them irreproducible when you go to another group or another astronomer or another algorithm. Because if you cherry pick your data, a different person could cherry pick different data and they'll end up with different results. So culling your data is really a very, very poor scientific practice.
I totally agree. I think you summed it up perfectly.
Very nice. Thank you. Well, this is turning out to be slightly longer than we were expecting. But do you have any concluding remarks of where we should leave the audience and where the collaboration is going?
I'm just excited for we're already working on the next data set. That's already in the pipeline, and I'm just so excited to see where that's going to go. And it's really a privilege to be a part of this project. And I've actually known David as long as I've been on part of this project. So
that's how we met.
It's exactly how we met. So this collaboration and this work always holds a special place in my heart for that, for the people that you meet throughout it. And it's like just such a privilege to be I'm very interested in VLBI as a subject, and this collaboration is basically like some of the people that created VLBI are in it, and it's like these world experts. So it's like, this is a great opportunity for people to learn about this fundamental aspect of the universe and the tools we use to discover it.
I couldn't agree more. I'm really glad you mentioned the people. We work with men and women who are at the forefront of science and technology. Telescopes like this in the background that's up at Haystack Observatory. Just the technology and the ingenuity of some of the men and women that are producing the hardware, the software, the data transportation systems, the correlation systems, the imaging algorithms. Obviously, you're a big part of that, Joseph. It's just phenomenal, and quite frankly, and the word is used way too much these days, but it's literally awesome. It inspires awe when you see just how amazing these people are and how hardworking they are, actually.
There's some absolute it's so the most amazing people I've ever met in this collaboration.
Yeah, no, we're very lucky. We see a whole breadth of humanity, both good and bad, but the good is really, really good. And we're thoroughly privileged, I think, to, as you rightly said, to work with some of these people. And we do have exciting results coming up, right? There'll be some polarimetry, so we'll be able to look at magnetic fields evolution in these systems. We'll at some point produce a new image of Sag-A star at the center of the Milky Way as well. That's super exciting because that thing spins in about 4 minutes. So the variation of emission is just going to be wonderful.
Our best chance to make a movie of a black hole too.
Well, a movie of a black hole, that really is the holy grail, right? If you can see photon emission evolve as the black hole is orbiting, spinning, which changes the fundamentals of cosmology, as you know, from Einsteinian to the Kerr metric, is just exciting beyond belief, and something I could not have imagined as a sort of childhood fan at 7 years old saying I want to be an astronomer. I could not have imagined we'd ever be able to make a movie of a black hole.
And don't forget space VLBI.
Well, space VLBI, that might be a few years away, but space VLBI, of course, extending those baselines to sort of hundreds of millions of kilometers, it is just going to be ridiculously exciting.
It might be a few years away, but we're working on it like right now.
Oh yeah. Oh no, I know we're working on it. I know we can't give away all our trade secrets, but yeah, it's the way to go. You want big baselines, you throw a radio telescope up on the moon or out there in space at the Lagrangian point to give you, million-mile baselines. It's going to be phenomenal. The spatial resolution will be just off the scale.
And the time resolution too. If you have a low Earth orbit, it's completing an orbit every 90 minutes.
Oh yeah, jeez. Yeah, amazing. I think I just thumped like a horse, and I heard the echo from the. That was quite funny.
Just regular David noises.
Regular David noises. There you go. So, okay. Well, this has been fun, and I think we're going to wrap it up.
All right. Thanks, everyone.
Well, this wraps up another presentation for Astraveo, where we go from geek to chic by sharing our passion and excitement for all things scientific, especially astronomy and in the mysteries of the universe. If you enjoyed this video, please hit the like button, and in the comments below, please leave us your suggestions for future presentations. We'll get right on it. And don't forget, you can join us on our journey by subscribing and hitting that bell. He's Joseph, and I'm David, and together we're Astraveo. Thanks for watching.